Hello, everyone. Welcome to our engineering webinar series. We hope that you are doing well. My name is Walter Cotto, and I'm going to be your moderator today, but I'm a customer consultant here at Elsevier. And, before we begin, I want to say if you have any questions, please ask your questions in the Q&A. We're going to have some time at the end of the session to answer those questions. And at the same time, as we go along, you also have the chat feature to talk to us a little bit, and we'll have somebody on our team reach out to you. So today we're going to talk about should high cobalt EV batteries be repurposed? And we're going to talk to Jessica Dunn, who is a Ph.D. candidate at UC Davis. However, before introducing Jessica and passing the mic over to her, I do want to speak a little bit about how we met and how Jessica came to work with Elsevier for this webinar. So a few weeks or a few months ago now, I watched a YouTube video and a documentary about, a lot of the waste around electric vehicle cars and especially the batteries. So I kind of started thinking, what kind of research is there out there? Who I would be able to collaborate with in my network, or how could I grow my network with people who are doing this type of research? So the first thing that I did there is I jumped to Engineering Village. As many of you know, you have access to Engineering Village, you're able to use it. And I looked for electric vehicles recycling, which, it's a new subject to me. I don't know too much about it, but luckily with Engineering Village, I'm able to see, what are people researching. So on the initial search, I got over almost 1,700 records, but then I want to summarize this search a little bit more and be a little bit more specific. Luckily, EV is helping me out here with the lithium-ion batteries. It's giving me this option already. I don't have to know or be an expert in the subject to know this, but I'm able to summarize it now to a more manageable number. Now, since I'm trying to find people in my network who are doing this research, the next step here would be to look for this research within the United States. So as I go here, I have the country and region options, and I'm able to click the United States. Now I'm able to just even limit it more to just people who could potentially be in my network or around my network one way or another. So you can see now I only have 94 records. It's a lot more manageable. I can download these records and really take a closer look into what the research looks like out there. But in this case, the fourth record here that comes up, this is one of the articles who Jessica was authored for. So that's how I found Jessica, reached out to her, and was able to, kind of get this relationship started. So with that in mind, before I pass it over to Jessica, I do want to put this poll up real quick. And if you guys can take just a couple minutes to answer the poll, it's going to help Jessica and our team to really see who's in the audience. So with that, I'll just leave you a couple minutes and I'll let Jessica share her screen.
Thanks, Walter. Yeah, thanks for giving me this platform. Okay, there we go. Can everyone see my screen?
Yeah, we can see it.
Awesome. Well, yeah, so I'm Jessica Dunn, as Walter said, and I'm really excited to talk to everybody today. The purpose of this presentation is really to discuss environmental impacts of two end-of-life routes for EV batteries that are high in cobalt. And so along that vein, the presentation is called Should High Cobalt EV Batteries Be Repurposed? Comparing end-of-life routes to achieve a sustainable circular economy. So as Walter said, I'm a PhD candidate at UC Davis, and I will be I research circular economy and lithium-ion battery recycling and reuse. And I'll also hand the mic over to Kabian Ritter, a colleague who's also a PhD candidate, but more in the realm of inorganic chemistry. And he's I would say, the resident chemist of our grad program. So I'm really thankful to have him help me with this project and be on here as well. So some just background information about EV uptake and end-of-life routes is kind of where I will start before going into the research I conducted at UC Davis, and a really important, aspect looking at what further research should be done to really answer this question. So with that, I'm first going to go over the benefits of EVs. My work is really focused on mitigating the negative impacts associated and with the batteries and with the electric vehicle as a whole. And I think it's really smart to go over the good before I start going over the bad so that we're on the same playing field. So firstly, the switch from internal combustion engines to electric vehicles can really have a decrease in the climate change impacts. You can see in the figure on the right there, the first column is internal combustion engines, so that's gasoline. It's a pretty high impact in the average, the red dot there. And the battery electric vehicle, the fourth column, is much lower. And so when we're considering that about like 30% of global emissions come from the transportation sector, and more than half of that come from private transportation, this is going to be a big global impact if we do make that shift. Along with the GHGs, we can talk about local pollutants. So these are the pollutants that lead to asthma and other health problems, and really impact low-income and minority populations that are close to living close to freeways or high traffic areas. In addition, reduced oil dependency is important. And with this switch to electric vehicles, there's really the opportunity to have more energy security. So with that, there's also hurdles to overcome in the transition to electrification and definitely impacts from it. So first off, EVs are very material intensive. You have to make the batteries using critical materials such as cobalt, nickel, manganese, and lithium. And when we're talking about critical materials and criticality, it's really the materials that are essential to the development of kind of renewable energy and this transition. And they're also materials that there's opportunity for some kind of geopolitical risk or the such to impact and disrupt that supply chain. And so cobalt is one that's really been pulled out because a high percentage, I think around 80%, come from the Democratic Republic of Congo, which you can see on that map is the blue country in Africa. And since it's so geographically central there, it's more susceptible to kind of geopolitical risk and the supply chain being broken. So along with that, there's also environmental and social impacts related to material mining. Cobalt is another one that's really an issue and talked about in this area. And that is because there's human rights violations associated with the mining, such as child labor. So just horrific kind of things that we want to mitigate. And then along with that, there's pollution, displacement, corruption, and conflict. So thirdly, there's also the issue of vehicles reaching end of life. These electric vehicles must be handled differently than internal combustion engines, which are the cars that we see using gasoline on the roads. Right now, there's a very developed kind of end of life route for these internal combustion engines. They're disassembled, the parts are reused, the parts are recycled. And this is going to be different for electric vehicles because the battery has to be recycled differently. It has to be handled with a bit more care. The materials are very valuable if we're talking about like cobalt and nickel. And so these are processes that are still kind of in the development phase to figure out how we're going to do this as a society. But there are, of course, paths to reducing these impacts and really getting over these hurdles. The first of which is repurposing. So this is when a battery is taken out of an electric vehicle and it's repurposed to be used in a stationary storage. And this stationary storage can support renewable, it can act in arbitrage. There's a lot of different purposes, but it's kind of one step of taking something and extending its lifespan. The next is recycling. So recycling is used to recover these critical materials that I've been talking about in the battery, really focusing on the cobalt, the nickel, the lithium, and the manganese, but also talking about like the copper and the aluminum. And with that, the materials that you've recovered through this recycling can be used in the manufacturing of new batteries and therefore kind of displace that needed virgin material. So that's where we talk about the recycled content of the battery. Lastly, but definitely not least, is the technological innovation that's happening. So I have two examples here, and they're definitely not all that are out there, but it's what I've used in my research and also I'm going to talk about now. The first of which is the cathode chemistry evolution. So you can see on this graphic on the bottom, there's NMC 111, which is kind of, I would say like the prominent NMC battery right now. And this is the cathode being used, and it's the nickel, manganese, and cobalt, where there's equal parts of all three materials. And basically what's happening is that the amount of cobalt is transitioning kind of to be a lower percentage, and nickel is used as a replacement. So the NMC 811 is 8 parts nickel, 1 part manganese and 1 part cobalt. And the reason for this is cobalt is the highest priced material. And it's also the most, susceptible to geopolitical risk and disruption in the supply chain. And there are also a lot of social and environmental impacts associated with it. So right now we're seeing a lot of the NMC battery 111 batteries retiring, or we're going to see soon. And the NMC 811 batteries are the ones that are going to be manufactured. Next is the use of silicone in the anode. So this is if you could look at the graphic on the right, it really looks at the energy density of silicone. And this is the benefit, is that the silicone is a lot more energy dense than graphite. So that means that you can use less overall materials for the same amount of kilowatt hours. So using less materials is definitely beneficial. And this is an innovation that we're not seeing on the market yet, but it's kind of in development and research. So this is, I'm talked about repurposing, recycling, and technological innovation. And this brings me to the waste hierarchy, looking at, what process should we go through first? This is something that Richa et al., which is the graphic on the right, has also looked at. And they found that, it's beneficial, you'll see, to maintain and reuse and refurbish an EV battery. And then it's best to do this cascaded use, where you use the battery in a stationary output, and then recycle the materials and use the materials for production of new batteries. And they're looking at this from an environmental perspective in the same way that I'm going to look at this as well. And so this is a great study, but what it doesn't consider is this technological innovation aspects, like what happens if we use, we are retiring high cobalt batteries, and the new batteries being manufactured have less cobalt or less material overall. And so that really brings me to the question of, should high cobalt EV batteries be repurposed, or should they be sent directly to recycling? And so this is the question of, should we reconsider this waste hierarchy due to this technological innovation? Great, so let's get into the study now that we have some kind of background. For my method, I used lifecycle assessment. Now this is environmental lifecycle assessment. So it's the study of the impacts through the life cycle of the product and the supply chains that support the product system. If you're familiar with LCA, I've used recipe as impacts. And so if you're not, that means nothing to you, but that's okay, because the midpoint impact categories are here in the gray. And those really, what they represent is kind of normalizing the impacts into certain categories to be able to compare two different scenarios that I have here. And what these impact categories represent are basically different levels of damage to the environment. So you can see when you're looking at midpoint impact categories, there's arrows going to damage pathways. So if you're looking at global warming, there's impacts to the respiratory system, there's impacts to the human health, to ecosystem, to resource availability. So this is a really important area, or basically method, to use when you're looking at life cycle environmental impacts. Great, so I did a comparative LCA for 2 end-of-life routes. So as I talked about, there's 2 kind of big scenarios we're looking at. The reuse scenario is one where the high cobalt cathode chemistry battery is retired from use in an EV at about 80% capacity. And then it's used in a second life stationary storage application. So that's the kind of the reuse, the remanufacturing. And then when it hits 50% capacity, the battery is recycled. The second scenario is this recycling scenario. So a high cobalt battery is again retired from an EV, but instead of being repurposed, it's sent directly to hydrometallurgical recycling. And then a low cobalt or a battery with silicon anode or this technologically advanced battery is manufactured for stationary use. And then that battery is again used until 50% capacity when the battery is recycled. So the functional unit, which is an LCA, a way to basically normalize and compare, is the provision of 1 kilowatt hour of electricity by the battery in its stationary use. Great, so that was probably a lot of information. So I'm kind of gonna go over it again in a different way. An LCA system boundary is really setting up the boundary so we know exactly what is being calculated in the environmental life cycle assessment. And so in the recycling scenario, the one on the top, I'll point with my cursor, we can see that that we're excluding the EV production and use, and that is for both of these. And that's because in both of these scenarios, there's going to be the EV and there's going to be the first life use of someone driving their EV. And that's not something we need to look at because we're just looking kind of at these like end of life routes. So the EV is recycled and then the materials are recovered. So that's credited back to the system. And then at that point, a new battery pack is produced. It's used in a stationary storage use. It's basically recycled and the materials are recovered again. In the repurposing scenario, the EV production and use is again outside of this calculation, but it is repurposed. It's used in a stationary storage use again, it's recycled and the materials are credited. You'll also see that connection of LIB packs, HVAC, and the housing of the stationary storage use is external to these calculations. And that's also because, it's a comparative LCA, so we need to compare apples to apples. And since both of these systems have those connections of the housing required, we can exclude them. So the technological innovation, right? That's like a key to this assessment. And that comes in the recycling scenario when we're producing that stationary storage pack. So the parameters of the pack change to look at the impacts of cobalt content. So I looked at NMC 622 or NMC 811. So these are 2 different kind of lower cobalt batteries. Also varying levels of the amount of recycled content within the battery. So this recycled content will just have basically less of an environmental impact because it's from recycling and not from mining. And then looking at what are the impacts of a silicone and graphite anode. Another really important aspect is how I modeled the stationary storage use phase. So the battery is being charged by solar power, same for both scenarios. The difference comes into the lifespan and the performance of that stationary pack. So for the pack that is being repurposed and used in a second life, it's going to be going from 80% capacity to 50% capacity, while the battery that is being manufactured and is new for that stationary storage use will go from 100% to 50% capacity. Now they don't go at the same rate during that whole lifespan. The degradation doesn't go at the same rate. So that's also really important to calculate when you're looking at like what are the kilowatt hours that are being used in the stationary storage use, which you'll remember is actually our functional unit. So basically what happens is you see this knee around between 70 and 80% capacity where the degradation rate starts to fall. So that was included in the calculations. Great, so I'm going to hand this over to Kabian. Kabian, you want to present on the lithium-ion battery stoichiometry?
Alrighty, well, thank you all for first, can everyone hear me?
Yeah, you're good.
Yes.
Okay, perfect. Okay, well, good morning. My name is Kabian Ritter. Thank you so much for taking time to hear this presentation. I guess I'll be talking a little bit more of the nitty gritty of how we actually went about calculating these different stoichiometries or these different chemistries. So we have 6 different cases, as you see here depicted in the middle. We have NMC 111, which is the traditional equal ratio amounts of the nickel, manganese, and cobalt, as well as the 622 and 811. And so those 3 different cases, we also changed the work of the anode, which would be graphite in one case, and then we have silicone for another case. So that gives us a total of 6 cases. And essentially to figure out our chemistries, we used it based on this very well-known equation at the bottom, which allows us to take the sulfate precursors of the metals to be able to control the amount, or the 111 or the 622 or the 811, those numbers that correlate to the amount of nickel, manganese, and cobalt that we add accordingly to our system. And so using this equation, as well as a lot of other acrobatics of chemistry and math that I won't bore you all with, we were able to find a reliable way to come up with the chemistries and the precursors that we would need for our life cycle assessment. We also were able to, model the change of from graphite anode to a silicone anode, again, mostly based on the fact that the energy density difference, between graphite and silicone is so drastic. So we're able to model a battery in a case in which the silicone anode, we use a lot less of the material because it has such a higher energy density, which is ideal, one of the ideal scenarios in the case that we were using a silicone anode. Another point I do want to point out here is that while we did change the chemistries of the NMC ratios as well as the anode composition, we did use simplifying assumptions to make sure that the mass changes to the overall cell were constrained. So mainly focusing on the fact, as well as ignoring the fact or keeping it out of our scope, that copper and aluminum are a part of the cell. So we kept those constrained across all of our modeled systems. So all 6 of those have the same amount of copper foil as well as aluminum foil. And we kept the overall mass of the battery pack constrained. So where mass changes are only reflected as a function of the change in chemistries and change of the anode and cathode. So that was the essential, I guess you could say, methodology as far as how we went about scientifically, or like the chemical acrobatics of changing the composition of our different batteries. It was something that was really important because we needed those different values to be able to model our life cycle assessment fully, as well as the byproducts as a function of the chemical equation. As you see here, the NMC one is the hydroxide precursor that's produced in this equation that we're showing, as well as some byproducts. And so those byproducts are also important along the way to keep track of, because they're also something that we consider as a part of our overall modeling. And I will pass it back to Jessica.
Yeah, thank you, Kabian. I'm very grateful for Kabian's expertise in chemistry because, as you can see from our interests, I am more in the industrial ecology side. So thanks for explaining that and for doing that work. So now I'm going to dive into just preliminary results. So this isn't a published paper yet. This is work in progress, which I think is great and really exciting to present to everyone, because it'll be a future to come paper. So let's dive in. First, the question of, should we recycle these high cobalt batteries, or should we continue to kind of look at reusing them? And we're going to look at it from a perspective of just transitioning to a lower cobalt battery and not really considering that silicon anode, or considering that recycled content. And as you can see from the right, repurposing has much lower impacts. I think that's pretty clear in all impact category, or in all indicators. And right here, you're only looking at global warming potential is the first bar graph on top. And so then there's human toxicity potential, and lastly, mineral depletion potential. And I've just pulled these out basically because they're indicators I think a lot of us like in the LCA world kind of like to talk about. Global warming impact, of course, is very important. Human toxicity is kind of the like toxicity to people's and their health, and mineral depletion, right? We're looking at very essential minerals. So how fast are they depleting? And the reasons that repurposing has such a lower impact than recycling, if we're just considering going to a lower cobalt battery, is really because the manufacturing stage is still very, very impact intensive, right? And so there's a lot of energy usage. There's also still virgin materials that are required in the manufacturing. And the comparison of an NMC 111 to an NMC 811 actually increases a lot of environmental impact categories due to the increased amount of nickel. So nickel isn't impact free, right? And so maybe, yeah, we'll talk about that going down. But the next thing we want to look at is what was the impact of using a silicone anode? So repurposing batteries is still the ideal situation. You can see that's still in the negative. But when you look at the graphite and the silicone comparisons of this recycling scenario, you can see that silicone is a lot less for the global warming potential, the human toxicity potential, and only slightly for the mineral depletion potential. So that's kind of just I guess a side point of the findings in this analysis is that you know, repurposing is better, but it looks like silicone anode has you know, less impact. And lastly, what if recycled materials are used? So same finding, repurposing is better in all impact categories beyond just the ones listed in these on this slide. But what we do find from this is also that using recycled content really 100% in this scenario really reduces all categories a lot more than the other category, the other transitions that we've seen. So using recycled content reduces the impacts more than transitioning to a lower cobalt chemistry, and also more than using a silicone anode. Great, so what were the conclusions of this question? Just a reminder, the question kind of was like, what should we do with these high cobalt batteries when there's a transition to lower cobalt and more or less material intensive batteries? Should we reconsider this waste hierarchy that is really known in the field of reusing and then repurposing and recycling? And the answer basically came to be that from an environmental perspective, no, we should continue reusing them and extending the life cycle or the lifespan. The impacts of the batteries are really reduced from using the recycled content and also from the silicone anodes. That's just kind of like a side note of the finding. And lastly, does this research capture the whole picture? So I would say no, it doesn't at all. It's only one piece of the puzzle, right? So just to reiterate, we're looking at the environmental impacts. We're not looking at the other kind of impacts that I listed, such as the social impacts, which are extremely important. Those being that, you know, there's displacement, there's human rights violations, there's corruption, there's conflict. There's a lot of issues with the mining of materials. And these are something that can be measured. There's social LCAs that look at assessing these impacts, and they're really extremely hard to characterize and measure, but they can be done. And I think that's kind of like the next phase of this research to really to answer this question of what should we do with batteries that are high in cobalt that are retiring when there's these new technologies that are less material intensive. Great, well, thank you. I would love to answer questions, and also I have my email there if you ever want to reach out with more questions or to discuss or work together. So I'll hand it back to Walter.
Perfect, thank you, Jessica. I think I learned a lot, so thank you for coming on today. So we are out of time, so we won't have time to dig into the questions today nearly as much. However, I do want to remind everyone, we're going to have our next webinar on May 19th and it's going to be a sustainable infrastructure and uncovering some of those trends in that subject. So once again, you can reach out to me if you have any questions. If you want to watch this, this is going to be on YouTube as well. You can reach out to Jessica as well. So this video is going to be up on our YouTube page. Please feel free to watch any videos. And yeah, so if there's any questions, please reach out. You can email me and I'll get those over to Jessica and we'll be happy to answer those. But thank you, Jessica. Thanks, Kabian, as well, for joining us today and speaking to our audience.
Thank you for
Yeah,
having
thank you
us.
so much. Yeah, thanks. Sorry we didn't leave time for questions, but you can definitely email me if anyone's interested.
No worries. Thank you.
Bye.
All right, take care, everyone. And everyone have
Have a
a
good one.
good rest of your week.